chords. What do we know a chord is from yesterday? Good? Okay, so it's a segment that is going from one side of the circle to the other. Okay? Is a diameter a chord? Yes. Are all diameters chords?
Yes.
Yes. Are all chords diameters? No. Very good. All right. Now, an arc, basically what an arc is it's a piece of your circumference. When we talk about arcs, they don't have a unit of actual length. So their units are not feet or inches or centimeters. They're actually degrees. So when we talk about arcs, we're going to talk about degrees. Okay? So we got pieces to the circle now. More so than just a diameter and a chord and everything we learned yesterday. All right. Center, that's in the middle, right? So if I want a central angle, shouldn't that be an angle whose vertex is on the center? Because if it was anywhere else, would it have a relationship to the center? Nope, it wouldn't. So central angle, the angle whose vertex is the center of the circle. Okay? Now, you notice we have what's called a minor arc and a major arc. Minor means what? Small. Major, big. All right. So, anybody want to guess how the minor arc relates to figure out a degree? Where would we get it from? Like for the arc or the central angle? Okay, good. The central angle, yeah, we'll usually talk about from 1 to maybe 180 degrees. Yep. How are the minor arc, those degrees, going to relate to the central angle? Do they have an idea? How is the hypotenuse the longest side? It's across from the biggest angle, right? So, what's the relationship going to be with the minor arc and the central angle? Now remember, they're both in degrees. What do you think? Knowing that stuff about the hypotenuse. Just see if we can use deductive reasoning here. Anybody have a guess what the relationship will be? Hint, look at how it's formed. Look at how the minor arc is formed. Ethan, what do you think? It's across from the central angle, right? So if I say the central angle, let's just say that it's 42, what's the degree going to be of the minor arc? How is it formed? How is the minor arc formed? From the what? From the central angle, right? And what's the degree of the central angle? 42. So the minor arc has a degree of 42 because that's how it's formed. So, definition. Minor arcs, that's an arc that is smaller than half of the circle because minor means small. And then the measure of the minor arc is defined to be the measure of the central angle because that's how it is formed. Bottom line. The two radii coming from the center, if you look at what's included there, that's the minor arc, and that's how it's formed. Does that kind of make some sense? Thinking back to kind of comparing it to the hypotenuse, why it's the longest side, because it's opposite the largest angle. Does that kind of make sense relating it to that? Major arc, what does that have to be bigger than if it's a major. 180, yep. And if I knew my central angle and my minor arc were 42, how am I going to get my major arc? Take 42 away from 360. Very good. So, definition of a major arc. An arc that is larger than half the circle. The measure is basically taking 360 and either subtracting the central angle or the minor arc because really they're the same. So, 360 minus 42. So we got. Good, 318. And that would be the major arc. Questions on what a central angle is or the difference between a minor and a major arc? Okay. If I were to ask you what a semicircle was, could you give me a definition? Half of a circle? Okay. What else? Part of a circle? Okay. Can anybody give a little bit more of a technical definition? Now seeing terms from yesterday and today? Just curious. Half of a circle is perfect. If you want to write semicircle, half a circle, that's perfect. Let's see if anybody can use the new terminology. So think of what half of a circle actually means and try to put it with the new terms. Kind of. Yeah, kind of. Minor arc, major arc. No? Kind of, yep. Picking those two apart. So. And what kind of arc of a circle? Kind of. We kind of want to steer clear of classifying a semicircle as minor or major because of the endpoints. What are the endpoints of a semicircle? The diameter. So, a semicircle is an arc whose endpoints are the diameter's endpoints, and that's what your book defines that. Now, I'm just asking you these questions to see if we can kind of put stuff together. If you want to write semicircle, it's half of a circle, perfect. That's fine. But good putting these things together. Alright, so any questions up to this point? Silence means no. Assuming? I'd like some sort of. Alright. Okay. Yesterday you learned what it means to be congruent circles. And what does that mean? Same radii. So now, what would it mean if I wanted congruent arcs? Same central angle. Alright. Let's come back to that in a second. So, congruent arcs, basically, you just have the same measure. You have the same central angle. Very good. So, you could have a picture like this, where these would both be 68, or you could split it up. You could have two of the same size circles, but you just have to pay attention to their radii. So let's call both of those 2. And then I could have this one like that, this one like that. But as long as their arcs are the same, they're congruent, but in 2 different spots. Yeah. Yep, they do. So they do have to be congruent circles to have congruent arcs. Yep. they're not exactly vertical angles, but those kind of look like vertical angles, right? Do these have to be vertical angles in the same circle to be congruent arcs? No, because what can we do with all of our radii? Move them and they're still the same size. Good. All right. Do we have that okay? So basically, bottom line, congruent arcs have to have the same measure, i.e., they have to have the same central line. That's what it all comes back to, right? All right, now, we have to be careful with how we label things, right? When we had angles to start with, we could not always label them with just one letter, right? Same thing kind of applies with these arcs. Minimum, how many letters do you have to be an arc? Minimum. You have to have 2, because you have to have the endpoints. Okay, so looking back at this slide, and this is the symbol now to represent you have an arc. It's actually a little arc. So if I want to know the measure of an arc AC, do you think we're talking about this guy? Or do you think we're talking about this guy for arc AC? If I know it's 60 degrees. Which one? The small one. Okay? So the small one is AC. So let's jot down for a minor arc, you need 2 letters. Minor arc, 2 letters. Okay? What would I need then for the major arc? I would have to have a minimum of 3. So it'd be like this. Where you have arc AC still being 60, but now I want to know the measure of arc CDA, which, what is that degree? 300, because it's 360 minus your central angle. So now for a major arc, jot down, you need 3 letters. Okay? So I don't want to label both a minor and a major with 2 letters because really I could be talking about either one, right? Oh, it does. As long as you have the arc, that's fine. Now, I said CDA, but it's written as ADC. Does that matter? Is it the same arc? Absolutely. Yep. Alright, so labeling and the symbols make sense? Central angle and how we get the actual arcs themselves make sense? Alright. Alright, more writing. 4 more theorems. Okay? We have writing and we have drawing. Okay? Gotta stick with me. Alright, first one up. Theorem 10.4. In the same circle, or in congruent circles, 2 minor arcs are congruent if and only if, we haven't seen that in a while, if and only if their corresponding chords are congruent. So what does that if and only if mean? Ethan? It's true forwards and backwards. Very good. So I could say, if 2 minor arcs are congruent, then their corresponding chords are congruent. Or I can say, if 2 chords are congruent, then their corresponding minor arcs are congruent. If and only if. Works both ways. Okay, so besides a circle, what do you need in this picture? What? Say louder. Yeah, you need chords. Okay, so let's go ahead and draw. It should look something like this. Now remember, we can work with this theorem forwards and backwards. So, which way is labeled in the picture? The statement itself or the reverse? And what do we call the reverse? The converse. Which one do we have here? What's labeled? congruent chords. So which way do we have? Do we have the statement itself or the converse? Yeah, we have the converse. So if I have two congruent chords that are the same, I was redundant, what's true? And be specific. Let's get the symbolic notation. Which two, though? You gotta be specific. Yeah, very good. So this means arc AB is congruent to arc BC, or vice versa. Does that make sense? 10-4? Okay. Okay, so please make sure you draw that picture and write that notation at the bottom. And then we got 10-5. If the diameter of a circle is perpendicular to a chord, then the diameter bisects. Now, what does bisect mean again? Cuts it in half. Very good. It bisects the chord and its arc. So it's actually bisecting two things. So besides the circle, what are we going to have to draw here? We're going to need a chord and a diameter. So there's the picture. And how do I know that they're perpendicular? The 90-degree box, yep, the right angle. So we got our diameter down the center. We got it being perpendicular to the chord FD. So what does this all mean? That's you. That's all we get from the beginning. So that's the if statement. So what do we get for the then statement? Okay, that's one thing we get. That ED is congruent to EF. And what's the other thing we get? There's an and. Not quite. Not quite. I don't. Say it again. And what are those? Well, okay. We don't want to say that a chord is congruent to anything other than a piece, another piece of the chord. Okay, so segments are congruent, and then arcs are congruent. So Ryan, what's the other piece? What are those? They're arcs. So arc DG is congruent to arc FG. So you got to make sure you're specific on what these things are. You can still use tick marks, yep. So write that symbolic notation up, please. Everybody got the picture? And the symbolic notation. Make sure you're putting those arcs over DG and GF. Okay, because they're not segments. Got it? Last two. So I want you to write 10-6. Leave a space for the picture. Write 10-7. So 10-6 says, if a chord is a perpendicular bisector of another chord, then that first chord is the diameter. Second one says, in the same circle or in congruent circles, two chords are congruent if and only if, so there's another one of those, if and only if they are equidistant from the center. Equidistant, we haven't heard for in a little bit. What does that mean? Same distance, yep. Ready for the picture for 10-6? Okay. So if it says, if one chord is the perpendicular bisector of another chord, what are you going to draw? Very good. Two chords that are inside the circle, but one is straight down the middle. And what is that one going to be from all of this? The one in the middle. That is the diameter. So KJ ends up being the diameter because of this notation right here. What does this actually tell us about? We have two tick marks and a right angle box. What does that tell us? That you have a perpendicular bisector. Now, which one is the perpendicular bisector from this notation? JK. Very good. Now, I have a question. Could I do this and still use this theorem? It would still be perpendicular. Can I use this theorem? Why not? How do we know it's not going to bisect it? If I have no numbers, nothing on there, how do I know that it's not going to be bisected? Okay, yes, it's one shorter than the other. One a little bit more specific. Joey? Very good. It's not going through the center of the circle. So we know if it's anywhere else, one side is going to be more than the other. Very good. Any questions on that theorem? Okay. Equidistant, we said that it means it's the same distance away, right? Here's the picture that you need. So we have circle E. We have two segments AB and CD. Those are going to be congruent if what? And don't just tell me that they're equidistant. I want you to be specific. So AB and CD are congruent because of what? So I'm kind of writing the notation already. AB is congruent to CD because, fill in those three blanks. That's more than three blanks. I'm using the actual letters. So I want more letters. So if you're correct in saying that they're equidistant, well, let's get some letters in there. Well, but this doesn't talk about eights. It's just talking about the chords. So we're looking for AB is congruent to CD because, and it's going to be three blanks. We need some letters in there. What two things are going to have to be congruent if it's true that the chords are equidistant from the center? Think what you think. Very good. Very good. That's what it means to be equidistant. That these two right here are the same length. Does that make sense? That's being specific on how they're equidistant. Any questions with that? Do you guys get what I'm saying by just being specific about being equidistant? Okay. All right, so let's put this to actual, get some numbers in there, put this to work. Now, remember, any theorem I give you, do I care what the name is? Do I care that you know what the name is? No, I care what? What it means. Okay, so we have 10-4 talking about if you have two congruent chords, their corresponding arcs are congruent, or vice versa, right? Here we have if a diameter is perpendicular to the chord, then it bisects the chord and the arcs. Here, a diameter is a perpendicular bisector, and then here, either way, two chords being congruent, they're equidistant from the center. So, put that to work here. Raise your hand if you can tell me what we have in the picture. What's going on here? Ethan, what do you have in here? But what do you have? Very good. We have two congruent chords, AD and CD. Okay, so if those chords are congruent, how are we going to get what x's? Those x's are in our arcs. So what do? You set them equal, and that's that first theorem we wrote down. So 2x is equal to x plus 40. What's x? 40. But our answer is not 40. Our answer we want is what is arc AD. So what is arc AD? It's 80 because you just plug it back in. Does that make sense applying this theorem? Okay. Now the next one, don't shout anything out. Really look at this. Okay? What you have is you're going to find what CG is. You know that AD is 40, and you know CD is 25. A lot of things going on here. So see if you can solve for CG. Try to solve for CG. Do you have the answer?
Yeah.
One second. Let everybody else get there. 1 second. Is anybody stuck? Where to go? Okay, so no one's raising their hand. All right, so what did you see right off the bat? I don't want an answer yet. I want to know what you saw right off the bat. Sorry, there's F in there. So AF and FD are both 20 because we can break that up because they're marked congruent. Very good. What else did we see first? What? Okay, how did you know, though, that it's a right triangle? How did we know that we can, in fact, mark that as right? Well, yes. It is about 10.7, but it doesn't specifically say in there that they're perpendicular, right? But that theorem says that the chords are what from the center? Equidistant. How do you measure something? Straight to it. When we go straight to it, you'll form a perpendicular line. So that's how we can make that be a right triangle. Now, why am I only working with that left side? I've got to solve for CG. Very good. You know that those two are congruent. So by using what? Pythagorean theorem, we can get CF to be 15, which is what X is. How many got to that? Very good. Does that make sense now if anybody was stuck a little bit? All right. There's your homework.